everybody. It is my great pleasure to announce Virginia Wright, that goes by Ginger. Virginia Ginger is running a very hot topic of cyber-informed engineering that now the lab is becoming international leader in. Virginia is a manager, the Energy Cyber Portfolio, CyberCore, at Idaho National Laboratory. And without further ado, I give mic to Ginger. Ginger, take it away. We are really happy.
Thank you, Dr. Manek. And hi, everybody. Good afternoon. My name, as Dr. Manek said, is Virginia Wright. I go by Ginger, and I'm going to talk to you this afternoon about cyber-informed engineering. And it's a topic that the laboratory is really excited about, and it is on the border between cybersecurity and engineering practice, which is a place that hasn't gotten a great deal of attention. So with this research and this work, we're trying to shed a light on where engineers, if they are informed about the ways that digital technology could either fail or be sabotaged by an adversary, might bring additional engineering grade solutions to help with system defense, mitigating the impacts of an attack, or may find ways to reduce the avenues that an attacker has to cause damage. So let me describe that a little bit. Cyber-informed engineering uses design decisions and engineering controls to eliminate or mitigate avenues for cyber-enabled attack. It offers the opportunity to use engineering to eliminate specific harmful consequences through the system design lifecycle, rather than adding cybersecurity controls after the fact. Most of our materials and the things that you read if you pick up our strategy or implementation guide are focused on engineers and technicians more than cybersecurity researchers. It's not that we don't want to include our cybersecurity population, but we also want to bring engineers into the conversation to try to address the solutions that only they can provide. And the final point on cyber-informed engineering is that we hope to create a culture of security that is aligned with the culture of safety that is already well known in industrial control systems applications. So that's a lot of words. Let me give you an example of what cyber-informed engineering looks like in practice. And I know that many of you, all of you, are customers of a municipal water system. You go to your tap, you turn it on, you fill a glass, and you expect that water to be available, clean, and safe to drink anytime, any day that you want it. But as you might know from watching the headlines, there are cyber adversaries who may have an interest in attacking those water structures, or there may also be opportunities for municipal water companies to become victims of ransomware attack. So something that may not have been intended for them, they may become a victim of. So clearly, this system is one that might be attacked by adversaries. We had an opportunity to talk with a municipal water provider recently. And of course, municipal water providers are also funded by your water bill. And if you look at your utility bills, the one that is likely the smallest is the water bill. They do not receive a great deal of funding for the work that they perform. So they are usually very small and have very, very little staff to do the work that they have to do. So automation is of high interest to them, especially when it might allow them to do more with the staff that they have. So we talked recently to a municipal water company that was exploring how to use a cloud solution that would let them monitor all of the pumping stations. And these are stations that keep the water pressure in the pipes within the city and ensure that when you open the tap, the water flows instead of dribbles or nothing comes out. And so they wanted to monitor those pumping stations remotely. And if there was a problem, potentially control them through this cloud application, which is wonderful for the municipal water company because they no longer have to put a technician in a truck and drive to the place where a pump may be ailing or may need recalibration. The downside is if an adversary gets into that control system, the adversary can enact an attack where they could change what the pumps were doing, or in a worst case scenario, they could turn the pump on and off and on and off and on and off so fast that they could actually shear the physical parts of that pump. And that would be an 18-month replacement process for the water utility. So the water utility did some research in cyber-informed engineering, and they applied a solution. And instead of having, they could have someone who monitored the tool, and they were certain that the cloud provider also had security people, but just as an additional barrier, an additional layer of security, the water company put what is called a time delay relay in place in each pumping station for each pump. These are mechanical controls that basically, once a command is issued, they start a timer. And in this case, it was 20 minutes, so that a command cannot be issued one after the other after the other. It will only accept one command every 20 minutes. The cost of each of these is about $20. So for $20 per pumping station, this water utility was able to both use this digital tool that allowed them to do more with less, but also use a mechanical control to limit what an adversary attacking that tool could do. So the adversary could turn a pump on or off, and the water company might then have to turn it the right way again. But what the adversary could not do because of this time delay relay is destroy equipment that would have a long lead time to replace. So I love this solution because if you're on the cyber team, you might have come to this water utility with lots of advice about how to secure this cloud solution. But the one thing that's not typically in a cyber researcher's bag of tricks is, hey, let's use this mechanical control and let's take this opportunity for damage off the table. That's just not in our bag of solutions. So by bringing an engineer into the mix, they have a different set of solutions that applied to a cyber risk really could make a real difference in what an adversary can do. The challenge with this is today's engineers are not taught these ideas. They're not taught to understand how adversaries might go after the systems that they build. They understand the critical consequences of failure, but often they need advice from cyber researchers about how an adversary might take advantage of those opportunities within a system to cause effects that are undesired. And so those things are what we are trying to do with cyber-informed engineering. So I hope that example helped. In 2020, the Department of Energy was directed by Congress to create a strategy to describe a national approach for cyber-informed engineering, to write this down and actually create a plan for introducing these ideas in various aspects of our national infrastructure to aid in cybersecurity. So INL got to the Idaho National Laboratory, which is where I work, and I can tell you about that if we have time at the end. But we gathered together a set of experts. We gathered government officials, we gathered academians, we gathered asset owners and operators, manufacturers, training organizations, and standard organizations. And we talked about these concepts together for about a year. And we produced collectively the National Cyber-Informed Engineering Strategy. That's available on the internet if that's something that you'd like to read. The most important part of it for me is the pillars that these advisors suggested that we think about when employing cyber-informed engineering and informing the population about it. So first, they encouraged us to make sure that there was an awareness of what cyber-informed engineering was and how it differs from our current cybersecurity protection capabilities. The pillar that most applies to you, they encouraged us to embed these ideas into formal education, training, and credentialing to help to ensure that engineers are taught these concepts and can work with their cybersecurity counterparts to apply them. They wanted us to develop tools. When I grew up, no engineer was an engineer without a slide rule, and some of you in this room may have to Google to find out what that is, and that's okay. Go ahead and do that. But every engineer needs tools. Today, you have modeling systems, you have simulation systems, you have advanced calculation systems that help you understand the impact of how systems will work and where failure modes occur. And we have to build similar tools for cyber-informed engineering. Then they encouraged us to apply these ideas both to the current infrastructure that exists today, especially the important infrastructure that ensures that Americans stay safe and have their needs met, but also to apply this to future infrastructure, particularly that infrastructure that is right now written on a cocktail napkin that someone takes into the Department of Energy, submits a proposal to create the next Diet Coke and Mentos reactor. I'm sure we can create power if we put enough Mentos tablets in Diet Coke and we get the foam. Anyway, whatever the new energy infrastructure is that is being researched and developed now, the sooner the engineers that are putting the research together and then the pilot concepts begin thinking about how an adversary might cause undesired operations within these equipment designs, the sooner that we can begin putting mitigations to limit what an adversary can do. So those are some exciting places to bring these ideas to life. In support of their charge that we bring these ideas out, we started by taking the 12 principles of cyber-informed engineering and documenting what they are and what they mean. And I'm a big believer that you learn more from questions than you do from answers. So our goal with each of these principles was to almost dehydrate each one into a critical question that if you were armed with that question and some design that you were considering or concept to analyze, you could then yourself apply that principle in the best way. So our first principle for cyber-informed engineering is consequence-focused design. When we're executing that principle, we're thinking about how we understand the critical functions the system that we are designing must ensure and the undesired consequences it must prevent. And typically, this is something that an engineer is very plugged into, but often our cyber researchers might know a lot less about this. They understand how the system works and the protection and mitigations that might make sense, but they don't always understand what is the core function that this system has to do in order to be successful for the organization, and what are the undesired consequences or undesired operating modes that the system could get into that would be bad. And I'll give you an example here. If I have a tank and I am applying temperature and pressure to change the state of whatever is in the tank, maybe I'm boiling water or whatever I am doing, my system has to ensure that that tank stays at the critical temperature that's right for whatever my process is. And the things that I have to prevent the tank from exploding due to overpressure. I have to prevent the material inside the tank from getting out and hurting people. And those are the critical functions that this system performs. So knowing that, I can begin to say, where might I need to put controls, and that's our next principle, that might reduce the opportunity for an adversary to take advantage of digital systems and change how that system works to cause damage. So once we understand our critical consequences, we begin looking at how we can implement controls to reduce avenues for attack or the damage which could result. In this control scenario, we are looking primarily, or we're looking from physical deterministic controls all the way across to digital controls. So if I can put a pressure relief valve on my tank so that when the pressure gets too high or the temperature gets too high, some matter is released in a safe way, or the tank can vent off in a safe way, well, that would limit what an adversary could do if they attacked that tank with the purpose of causing that specific kind of damage. Now, is that the only control I should have in place? Absolutely not. I should probably monitor the network and the specific functions through which an adversary might approach this tank in order to do the damage. And so that is how we might bring together our engineering controls that we can produce physically and the cybersecurity controls that help to defray possibility for attack. The next element is a secure information architecture. And if you are on the cyber side, if you are on the IT side, we do this every day. We know how to create a network architecture. We know how to segment data and protect important aspects of the process. But often our engineering counterparts might either be able to highlight additional data that, if manipulated, could lead to system consequences that would be undesirable, or they might be able to help us understand areas of the process where data causes core changes in how the process is performed, or what is happening to, again, I'm imagining my liquid in my tank, where might data cause that tank to empty or fill? And how do I control and validate that the data going through my architecture has not been manipulated or changed by an adversary? The next element is design simplification. And if I was with you in person, I would hold up my iPhone right now and I would say, do any of you fully understand all of the features of that particular system that we all put in our pockets and carry with us every day? And most of you would agree, no, we don't know all of the features that that particular system performs. And if someone ticked off those features, there would likely be some that I would say, you know, thank you, but I don't really need that feature, and I don't really need that feature. It doesn't provide me a benefit, and it creates an attack surface through which someone could impact me. But I don't get the opportunity when I buy my cell phone to pick which features I really want and which features I don't. It comes as a unit. In an engineering design, we do have some opportunities to look at the features of our system that we want and determine what is not absolutely necessary to the process that we are performing. And where we can design those out. Now, I'm having an opportunity to look across the Zoom at Dr. Manick, and I will say in doing this simplification, we cannot design out so many features that our system becomes frail. We must consider resilience as an aspect of our design simplification, and there is balance in doing this. But an over-designed, over-complicated system is often where an attacker gets an advantage. And often our engineers, when they configure features of the system, they will turn the features off on configuration menus and not recognize that although an inside user can't take advantage of that feature anymore, an attacker can still do so. It's still in the code base. It is still possible to leverage the functionality of that feature through an exploit, even when someone using the system through its operational menus might not have that button or that dial available to them. And so that's another important part of design simplification, is helping those engineers understand that latent functionality, what that means, and how they might work with vendors to see if there are opportunities to take out features that are not needed and remove the code base. The next element is layered defenses. And in practicing this principle, we are trying to create the best compilation of system defenses to defend the particular consequences that we identified at the early stages. And those will incorporate both physical design features that an engineer can bring to the table, and also the whole suite of cybersecurity protections that we can put there. And we are trying to look at how impactful the consequence could be, and how many of the features would actually help us either predict that a system might be approaching a consequential place? Is there an attacker exploiting aspects of the system which might be close to or part of the pathway that they would need to do to get to one of our critical functions? How might I leverage my firewall protections? How might I leverage monitoring and other system defenses in order to create the fullest suite of defensive capabilities? Like to that is active defense. Now that we understand what layers of protections are available to us, how can we actually proactively prepare to use those defenses? And this gets into the people side and the use side of the plans that we identified in layered defenses. So in active defense, we are thinking about what happens if. We're thinking about those consequences that we identified, and we are actually writing down, how might we defend this system? What would we need? What resources would have to be employed? What would that mean to my system processes? How do I understand what that would look like and prepare for it? In interdependency evaluation, and that's our next principle, because everything up to here, we've been thinking about our system and the direct consequences. But in interdependency evaluation, we start to think more about what feeds our system and what our system feeds. Where are there opportunities that an attack on a different system might have an impact on ours? And what do we need to do to defend against that? We already probably have protections on the engineering side for where a failure in a system would impact ours, but there may be things that an adversary can enact digitally that someone who designed the system feeding ours or the system we feed didn't think was possible. And so this is where we start to look more broadly at those interdependencies and think about defenses, whether those are cyber enacted defenses or whether those are physical defenses that we might need to put in place around those interdependency areas. Particularly, we are looking in this zero trust environment for areas of assumed trust between system elements that may be tied together in a common process. With digital asset awareness, the question here is a tripart one, and I apologize, that's messy, but I'm going to go through this with you. How do I understand where digital assets are used, what functions they are capable of, and our assumptions about how they work? This principle was brought to light in an exercise that I was able to participate in from my Department of Energy work. We had a power system that was at scale, and we had asset owners that we had put in place to defend this power system. And unfortunately for those power asset owners, we had pwned this system. Our adversary unit owned it left, right, and sideways. Not, can you find the one piece of malware, but we had it wired for sound. Our adversaries could control all of the different parts of those systems. And the first thing that our system operator did when faced with this adversary controlled network was walk into a substation and turn a switch that put it into manual mode. This is a very important way that power asset owners isolate potential digital controls that may affect a particular substation when they are in it. It cuts off the network. Well, it stops taking commands from the central office through the network that is connected to the control system for the substation. And so again, this is something that system operators do, and they understand that it puts them in control of the network. The way that they understand it, that is true. But when an adversary has put capabilities inside that system, what that asset owner didn't understand is that turning the switch to manual didn't take away all of the automation in the various components that that substation had. They were still automated, and the adversary still had a direct line to be able to control the functions that they had implanted. All the operator did was turn off the central office. They didn't turn off the adversary. But the person manning that substation had no idea that that switch didn't do magic. They really did think that it did because they had never really considered it before. So as he stood, arms akimbo, manning his substation, feeling like this was his defense, behind him, the adversary was opening breakers and closing breakers and causing power to flow in ways that were undesired. So this substation operator, a mature, talented engineer, someone that I would love to have in my power system, did not understand the functions that the digital technology they were using were capable of. He assumed that when he went into manual mode, that protective relay would be fully under his control. And so that's why these later questions are here. We have assumptions about how this digital technology works that we need to confront and understand in our design. And then we need to understand all of the functions that the digital technology is capable of, not just the ones that we want to use. And then finally, once we've got that in our design and we have used all of the other principles to put the right mitigations in place, we need to track where that digital technology is so that we can make sure that it is being patched and cared for appropriately by the cyber researchers or cyber caretakers who provide digital support for that technology, because the engineer will also take that for granted. The next principle is cybersecure supply chain controls. And most simply, this question is, now that we've thought about all of these things that are part of our system security, how do we ensure that the providers that we hire and contract with deliver the security we need in the products that we take in from them, in the services that they provide? This is a complex question because often those who operate the system are not those who actually designed it or actually built it. And so this is a complex set of relationships where everyone must agree on the same kinds of security. And we are only as secure as our lowest maturity or weakest provider in terms of the security that we get. And so this is a core set of thinking about how to communicate cyber-informed engineering out to your providers and how then you measure their effectiveness at performing those tenets. In planned resilience, we start to turn our what ifs into even ifs. This is linked very closely with the layered defenses and the active defense that we talked about earlier. But through this, we are thinking about, what if an adversary takes control of this? What if an adversary causes this consequence to happen? Do I have adverse operating plans that allow me to move into some functional, controlled operating environment where even with an adversary in my system, I can at least control the system I have? And if I am very effective, I can continue being productive within that system. And this requires complex conversations between engineers and between the cybersecurity team to understand the scenarios that could occur and put the right planning in place. But through planned resilience, we can then understand our staffing model, what that production would look like. How do we inform systems upstream or downstream from us about the effects that we're having and what that means for them? The next element is engineering information control. And I will tell you that my job at the Idaho National Laboratory is one of the most fun that I have ever had because we get to do a lot of assessments on both large-scale power systems, on individual components of those systems, and even on regional functions that are performed. One of the first steps that we do when we're called upon to do an assessment is we use our Google Foo and pull up information. What can we find on the internet about this organization, about this system, about who they're hiring, what skills do those people need? What can I find out from all of these disparate sources of information about the process that is being performed, about the systems that support that process? And then how can I use that to craft my white hat hacker attack on that system? And all too often we are aided in our search for information because the engineers and the designers of the system did not adequately control the information that was sensitive about that system, that was informational, that helped us plan an attack. Often we find engineering diagrams. There was a military base that we assessed in Virginia where I could find the admiral's office layout and get the full conduit and heating, ventilation, and air conditioning upgrade that had just been performed. The very proud contractor put all of that up on the internet. So I knew the version, I knew the system. And if I had really wanted to make it a hot day for the admiral, this would have been at least something that we could have planned out in some detail. So helping engineers understand what information about their system is important to adversaries, is useful, and how they can protect it, not only through the design process, but this gets excruciatingly harder. Most of our infrastructure deployments are out there for decades. And so we not only have to protect the design information while they are under design, but also throughout the system's life cycle. And even in retirement, I can take information about a system that was retired and begin to make assumptions about the system that replaced it. So as you become system designers on your own, please do not assume any of the diagrams aren't important. They are all worthy of being protected, because any little nugget of information, it's like working a Sudoku puzzle, any nugget of information can help an adversary. The final element of cyber-informed engineering is cybersecurity culture. As we begin to design systems, we want to ensure that it's not only the cybersecurity team or the IT team's job to secure that system. There are many, many people who touch that system who have a role. How about the procurement person who, in the example that I mentioned before, gave that small business contractor who put the system in for the admiral, gave them these detailed drawings so that they were then available to be put out on the internet by that contractor? How, if that procurement agent had understood how to brief or how to set requirements for that contractor so that they knew not to put that information out, that would have been a much better security result. But I bet the procurement person didn't really understand that they were the linchpin performer at that moment in cybersecurity. So through cybersecurity culture, we're bringing the engineers into the conversation about security and making sure that, armed with the information they have about consequences, they let various individuals know about the roles that they perform to protect the system in the right way. And again, it's not all the IT team or the cybersecurity team. So those are a lot of principles. And armed with this, our job in the past year was to write down a little bit more about cyber-informed engineering. It's great to have these high-level things, but what does that mean? What do these things mean in practice? So we had the opportunity this year to dive a little deeper, and I'm showing you a systems development lifecycle. It may be a little bit different from the ones that you've learned in the various classes that you have taken, but generically, this is a sample system development lifecycle. We took those principles that we talked about just now, and we took them across the different phases of the system development lifecycle and derived further questions for designers, for implementers, for operators about each principle through the systems design lifecycle. Because how I think about each of those principles at the concept phase may be very, very different than what I need to think about during the development, during the development phase, or finally in the operations and maintenance phase, how I keep this security going and how I keep it strong. So we created a guide that we have just published, which is the Cyber-Informed Engineering Implementation Guide. And I've got a link to it on this slide. If you search for it, you can find it. But in that guide, we start by describing the principles, and I gave you a high-level description here. This goes into a little bit more detail, and talking about how those principles change across the life cycle of design. Then we developed specific questions for each of the principles within the phase. Some of the questions are multi-part. Never let me close to designing an exam for you because it will be excruciating, I promise. But this allows a practitioner to think through for their design, where could they tease out areas where they can apply, again, engineering mitigations that will ultimately increase the security of the system. Finally, where we could, we gave examples of what it might mean to consider this question or apply this question on a design. Then at the very end of the guide, we worked with a water engineering company to create a case study. They fictionalized across several different projects that they participated in a real team applying cyber-informed engineering to an actual water system design problem. And I've got one example here where you can see they went through the various principles, and they even gave examples of what kinds of controls they might put in place to enact that principle. And then as you look at this, they even identified where in the systems design lifecycle they would perform that work, or where they would consider it. So if you want to go through this guide, I highly recommend spending some time with the case study. The questions are very important. They're there for reference. They're there to be read, but the case study will really give you a chance to get your hands a little bit deeper into this. So I've introduced you to cyber-informed engineering, and one of the things that's very important to us is keeping a rich set of participants involved, hearing from real engineers and real practitioners about how to apply these concepts. So in order to ensure that we have that stakeholder group, we have a community of practice that meets monthly, and our next meeting for our quarterly community of practice is the 11th of October. We also have formed 3 working groups that help us in 3 specific focus areas. And these groups get their hands dirty. They help us write documents. They give us core ideas that we build from. So the first working group is focused on standards. We would like to integrate these ideas into engineering and cybersecurity standards. Today, a lot of engineering standards look at the functional performance of a system, but many don't consider cybersecurity within the engineering structure. And we think there are opportunities to enhance that. We also have cybersecurity standards, which often consider only the digitally enacted cybersecurity solutions or mitigations which could be applied, and not always the engineering or design solutions that could be applied. And so we're looking at how we can put cyber-informed engineering into both. The second working group is focused on education. How do we bring these ideas into curricula? Would it be great to have a capstone assignment where certain students create a design and other students think of ways that it might be broken and they work together to enhance the design? Or would there be a class in this? Should there be a degree in this? That's what that working group wrestles with. And then we have a development working group. They helped us create the implementation guide and our open source library of resources that I'll talk about in a moment, but they also help us with the tools that an engineer would need to apply these ideas. So if you would like to join any of these working groups or take part in them, I'll give you an email address at the end that would let you be an active member. One of the fun assignments that we got this year for cyber-informed engineering was to look at what DOE, Department of Energy research has been done in this area. So we put together an open source library, and we found in that actually the Department of Energy has been thinking about this idea since 2013, so 10 years. When there was first the idea of a smart grid, there was a set of researchers who were developing ideas for workforce development. What kinds of staff would we need for this smart grid that was just appearing? And they talked about a cyber-informed engineer and some of the aspects of what that individual would have. So we were able to collect these items and put them out in a library so that you can browse just the DOE research that's focused on cyber-informed engineering. So if you are interested in that library or in the implementation guide or the other resources I've talked about, we have a website, and that is at inl.gov/CIE. You can find the things I've talked about here and some other articles, including a concepts video that Sans recorded with us, and several articles that we've written describing both cyber-informed engineering generally and its applications. Okay, I've got some, again, addresses here, some ways that you can contact me if you're interested. That CIE@inl.gov address would let you get into our working groups and participate in some of our discovery as you would like. So with that, I've given you a great deal of information, and I'd love to hear from you. Are there questions I can answer or comments that you have?
Well, thank you, Ginger, for this. Literally a wealth of information on a very hot topic that, as you said, has been around for quite some time. And now you're leading not only national, but international group paying attention and focusing on these problems. I have a pleasure of joining these regular meetings, and I can tell everybody that it's a great it's fun, it's scary, it's inquisitive, it's provocative, it's interesting in so many ways. So I would encourage you to make a contact or let me know and join the gang. Questions or comments, please go ahead in virtual world or here in the room.
The workforce development.
And just speak up.
Yeah.
I'm not sure.
So about the workforce development, are you like encouraging engineers or training them for this specific role?
So one of the core things that we are doing is, and I think the question that as I understood it was, are we training engineers for this specific role? So first, did I get the question right?
Yes.
Okay. So we're working on training engineers in a couple of different ways. First, we've got several universities that are looking at how to bring these ideas into their curriculum. Because the most important thing that we can do is ensure that all engineers who are taught and certified about the practice of engineering are taught about how to be cyber informed in their engineering practice. So that's number one. Number two, we are also working with engineers who work both at the Idaho National Laboratory and for various contracting organizations that build critical infrastructure. We're introducing them to cyber-informed engineering and helping them apply that in their practice. And then the third way that we are working is we take on direct projects as the Idaho National Laboratory, and we are putting cyber-informed engineering into practice in the things that we do in the reactors that we are building here on site and in our clean energy research.
Great answer. Questions, please. Yes, Costa, go ahead.
I'm just
Professor
wondering,
Domevsky.
I just have a quick question. How much of this can we automate, or how much of it is like a human factor? I guess most of it is a human aspect, but is there anything that can be automated?
So that is part of what we would like to begin discovering this year. I almost feel like we went back to the Stone Age in some ways to create the implementation guide, because we looked organically at questions and we wrote them down in book form. So I am very curious about injecting these ideas into modern design tools. One of the challenges with automation is that often undesired functionality and vulnerabilities are not documented within a system. And so if I have a model of that system, it may not include anything that was outside of the thinking of the engineer who created the model. And I can give some examples of that. So for instance, it won't have the vulnerabilities, but it also may not have the functionality working in ways outside of the model builder's idea of how it would work. And so that is one thing that we are curious about in automating this. Could we use modeling tools? Could we use simulations and find the places where we could best apply cyber-informed engineering? Could we actually use those tools to recommend discrete cyber-informed mitigations? Could we use it to traverse a pathway and get that right set of layered defenses for an impact that we could quantify? I am interested in all those questions, and if you have research ideas there, I would love to hear them and work with the Department of Energy to get those proposed. And that's a great question. Like I say, it's something I'm excited about, but it's something I'm curious about whether it's possible. And I told you I would give you an example. We had a cyber researcher who was modeling whether a cyber injection could result in a water hammer attack. And can I have a show of hands of, does the idea of water hammer, is that familiar to you? So if I have water in a piped system, if a sudden mass of that water flows across the pipe and impacts a function on the other side, that's a water hammer. And this researcher was trying to determine whether he could create a water hammer through enacting digital commands on a system. And because what he was working on was a very large scale system, he couldn't build one in his bathtub. So what he thought he would do is construct a very small example, but hook it to a model. And then he would have the model reflect whether or not his water hammer had occurred successfully. But the problem was the model builder for the system that he was working on did not include the idea of water hammers into the model that they built. So he kept trying his cyber attack and it kept not working. He kept thinking, well, suddenly, at some point, this is going to work. But then when he did research on the model, he found out it wasn't for that purpose. So they didn't include that functionality. And thus the model didn't show his attack working when, if he'd had a real system, it absolutely would have. So that's one of my questions about automation. But again, I think there's lots of good research and we should find out.
So, talk about like critical infrastructure. So how difficult is it to implement these practices in a legacy system where we have PLCs, we have systems that are like decades of year old?
Well, this is a thing of degrees. So I think it's not difficult at all to do the thinking and to identify where are the most consequential areas to begin putting in mitigations. And at that point, then it becomes a cost and benefit question. What are the impacts of re-engineering a system? What are the costs of the mitigations that we would have to provide? And where could we get the most benefit? As you mentioned, the systems being decades old, one challenge that I would issue for all of us to think about is that there are many asset owners today who presume that because their systems are old, they would be invulnerable to attack or uninteresting to an adversary. And of course, you all may find that because the systems are old, they are even more interesting to an adversary because they can leverage tools that are well understood to go after those systems. So that's something that we have to work with asset owners on. Many are thinking about the sunk cost fallacy. They cannot, because they already have the engineer or the infrastructure in place, they're having a hard time thinking about how to add these protections because it's not under design. It has been designed and it has been functioning. But we are working with some asset owners this year where we will be able to confront those assumptions directly. And again, thank you for that question.
Good questions flowing. Anyone from the world of Zoom? Or from the audience here? Guys, thinking I will mention the idea of bringing mechanical device into a mix is probably something computer science students do not necessarily always think about because we are focusing on software alone. Vice versa, computer engineering is the opposite. Maybe they're focusing on hardware alone, but not software. So it's the mix that works together. NRC, Nuclear Regulatory Commission, is very well aware of these things. Also over design versus under design, all these things that are unnecessary or seemingly necessary, but really not. And they're just simply a baggage that we live with and simply opening doors or windows for opening this vulnerability surface way more than necessary. I really like those reflections. Each of these CIE principles was, as you might have noticed, very carefully identified and explained. Now, Ginger, we don't have that much time left, but perhaps you could spend a few minutes talking about the INL opportunities when it comes to internships, working together. I understand that during COVID, you relaxed those requirements that these internships can be done remotely. I'm not sure if that is still the case, but can you speak to that a little bit, please?
I would love that. Thank you for that opportunity. So I work for the Idaho National Laboratory. It is one of 17 Department of Energy laboratories that exist. Some of our laboratories are single function laboratories, and I'll use Fermilab as an example. They do research in very specific particle areas. And some of the labs that we have, like the ones you've probably heard of, Idaho, Sandia, Livermore, Lawrence Berkeley, they are multi-program, Los Alamos, they are multi-program laboratories, and they do research across a wide number of areas. Each summer, all of the various national laboratories list internships. INL is among them. We have internships that focus in cyber physical systems. We have internships that allow you to build cyber physical systems, do research against them. That's one of the largest areas of our focus. And so we have many opportunities there. As Dr. Manek said, we have relaxed the requirements that would have you coming to Idaho. Although as a former Virginia dweller who came to Idaho, it's beautiful in the summer and we have very long evenings. So you'll enjoy the time that you're here and you have a chance to go to the national parks and other places and explore. So that part is great. And the research that you get to do is wonderful. But we do have both remote and in Idaho internships that you can consider. We will start listing those on our website, inl.gov, very soon. Typically, folks start putting those up around January, but you'll find a few intrepid souls who are already listing them. And we take applications on those throughout the year. I would also suggest if you find an internship that is something that may not be fully close to your the skills or what you want to do, but you'd just like to make sure that you get your resume into our system, go ahead and apply to that and let us get your resume. And that may open up opportunities for us to offer tailored internships that are specific to your interest areas.
Super awesome. You have one more question here
about these internships. So are these also available for international students, or is it US citizenship or permit?
So many of our specifically cybersecurity internships are not available to international students. However, our energy environment S&T group does offer international internships that would allow you to focus on research with resilient energy systems, EVs, and other aspects of our energy system. So there may be opportunities there that are open to international students.
He's nodding, which means they're interested. So that's a good thing. Last call for questions or comments. If not, please join me in thanking, which is right.